Hello, lab rats. Sorry I'm not seeing your faces in person today, but let's go ahead and get your lesson started. For class participation credit this week, you'll need to pay attention to all the ridiculously bad science jokes, puns, and riddles that I've dispersed throughout your lesson. Pick one that makes you laugh, snort, roll your eyes, or facepalm. Either you think it's kind of funny or it's so awful you can't believe I made you endure it. And make me a meme or draw me an image representing your pick. Post it to our forum under the established heading memes, which is in the students 2020-2021 chemistry forum. And the link for that exact post is in your Teacher Ease assignment for class participation this week. So we're discussing mixtures. What is a mixture and what are the types of mixtures? Mixture. A mixture is a substance made by combining two or more different materials in such a way that no chemical reaction occurs, so not a compound. A mixture can usually be separated back into its original components. Let's discuss the types of mixtures. So we have homogeneous, which are mixtures in which the particles are distributed very evenly and they're not easily separated. And we also have heterogeneous, where the particles are easily separated. So the types of heterogeneous mixtures. We have suspensions. Those are mixtures of a fluid that contains solid particles sufficiently large for sedimentation. Notice that we've used the word fluid and not liquid here because suspensions can be gases. Another type of heterogeneous mixture would be a colloid. This is a mixture in which very small particles of one substance are distributed evenly throughout another substance. What's homogenized milk? So unless you've gone to a farm and consumed milk there or bought special milk, if you're just getting your milk from the grocery store, you are very likely drinking homogenized milk. So here is a video to explain what that is.
Do you ever wonder what exactly is homogenized milk? Well, you're not alone.
Dear Organic Valley, I noticed that you have homogenized and non-homogenized milk. What's the difference? Great question. Here's one of our food scientists with the answer.
I'm Emma Grindy, a product development food technologist, and I've been with Organic Valley for 5 years. Homogenization is simply the process of breaking down fat molecules so the milk has a smooth and even consistency. Homogenization doesn't involve additives or chemicals, and homogenization doesn't alter the nutritional benefits of drinking milk. In its natural state, all raw milk is composed of protein, water, and butterfat. Left alone, the fat will rise to the top, creating an obvious layer of cream. This is where we get the saying, only the cream rises to the top. When milk is homogenized, it's heated, agitated, and passed through a valve at high pressure. This physical process changes the fat molecules so they are the same size and density as the rest of the milk. The result? Homogenized milk is always smooth and consistent.
That's really all there is to it. But if you would like to try milk with the cream on top, Organic Valley makes several non-homogenized dairy products. Grass milk whole milk, cream on top, grass milk 2% milk, cream on top, and our signature cream on top grass milk yogurt.
To find Organic Valley products near you, try our product locator. Till next time, Organic Valley.
The Tyndall effect. Colloids are often confused with true homogeneous solutions because the individual dispersed particles of a colloid cannot be seen. When light is passed through a solution, the dissolved particles are too small to deflect light. However, the dispersed particles of a colloid, being larger, do deflect light. The Tyndall effect is the scattering of visible light by colloidal particles. You have undoubtedly seen a beam of light as it passes through fog, smoke, or a scattering of dust particles suspended in the air. All three are examples of colloids. Suspensions may scatter light, but if the number of suspended particles is sufficiently large, the suspension may simply be opaque and the light scattering will not occur. Separating colloids. So blood is also a colloid, and this video explains how those tiny little capillary tubes of blood that you get taken at the doctor's office are separated using a centrifuge, and that can give information about how much plasma versus how many solid particles, such as red and white blood cells, you have. Types of homogeneous mixtures. Solution. A homogeneous mixture composed of two or more substances, a solute which is dissolved in it, and a solvent which does the dissolving. So the example here is carbonated water, and in this case, our solute is a gas dissolved in a liquid solvent. So this chart gives you particle size and then characteristics such as ability to separate, filtration, and whether or not a solution, colloid, or suspension will scatter light. So let's look at these examples and see what we think. Is this an example of a suspension, a colloid, or a solution? Here we have a suspension, because you can see that over time those particles do separate out. How about Jell-O? Jell-O is a colloid because it has very small particles evenly dispersed throughout a medium, and it's not easily separated. And how about air? Air is a solution. Solutes and solvents. The solute is dissolved and the solvent does the dissolving. Dissolving. Dissolution occurs when a solute breaks up from larger particles into much smaller groups or individual molecules. This breakup is caused by coming into contact with a solvent. Concentration. The concentration of a solution is the quantity of solute that is contained in a particular quantity of solvent or solution. Molarity. So when we talk about molarity and solutions, the most common unit of concentration is molarity, which is also the most useful for calculations involving the stoichiometry of reactions in solution. Molarity, which we abbreviate with that capital M there, is defined as the number of moles of solute present in exactly 1 liter of solution. It is equivalently the number of millimoles of solute present in exactly 1 milliliter of solution. So in this case, we have a picture here of acetic acid, and that would be 1 molar solution. And we have lots of solutions of different molarities in our lab storage closet. And this is the equation for molarity. It would be moles of solute divided by liters of solution, or obviously millimoles of solute divided by milliliters of solution. The units of molarity are therefore moles per liter of solution, mole per liter, and it can be abbreviated as shown here, mm. An aqueous solution that contains 1 mole or 342 grams of sucrose, for example, is enough water to give a final volume of 1 liter and has a sucrose concentration of 1 mole per liter, or 1 molar. So that would be how we write it. The universal solvent is water, and this has to do with the construction of the water molecule itself and how it behaves with polar and non-polar substances, as well as ionic and molecular compounds. Dissolving ionic and molecular solids. So right here is Himalayan salt. Compounds which exist as solid ionic crystals dissolve in water as ions, and most of them are highly soluble in water. The positive and negative ions spread apart and are surrounded by water. And that's cotton candy. Dissolving a molecular solid requires breaking only weak intermolecular forces, not the covalent bonds that actually hold the individual molecules together. Therefore, molecular solids are also relatively soluble in water. So let's look at your homework and notes. Here are the definitions. Yours don't have to be exactly like this, but I'll roll through them for you. Solution. A homogeneous mixture composed of 2 or more substances. In such a mixture, a solute is a substance dissolved in another substance known as a solvent. Suspension. A heterogeneous mixture that contains solid particles sufficiently large for sedimentation. Solvent. A substance, ordinarily a liquid, in which other materials dissolve to form a solution. Solute. A substance that is dissolved in a solution. Colloid. A homogeneous mixture in which the dispersed particles do not settle out. Concentration. The amount of a substance in a defined space or volume, the ratio of solute in solution to either solvent or total solution. Molarity. The number of moles of solute per liter of solution. And you can see why we use molarity more than concentration specifically, because concentration says it can be either solvent or total solution, whereas molarity, we know exactly what we're dealing with, which is 1 liter of solution. So how many parts per million of mercury are there in a sample of tap water with a mass of 750 grams containing 2.2 grams of mercury? So parts per million is a measurement of concentration. For very dilute solutions, it's weight, and weight volume concentrations are sometimes expressed in parts per million. Parts per million is abbreviated as ppm. 1 ppm is 1 part by weight or volume of solute in 1 million parts by weight or volume of solution. In weight volume terms, 1 part per million is 1 gram. Well, I'll just let you read through them all. And then here's how we work that problem out. So you should have 2.9 parts per million of mercury. How is a suspension different from a colloid? Suspensions will settle out if allowed to rest, but colloids will not. Suspensions contain larger particles than colloids. Blood is a suspension of different liquids and cells that have different densities. What is the best way to separate the different components of blood? Well, as we saw in our video, centrifuge. What is a molarity of a solution containing 0.15 moles of potassium chloride in 350 milliliters of solution? This is how you work out this problem. And your answer should be 0.43 molar. So now you can proceed to the portal in Teacher Ease and go ahead and complete the assignment there by making me a meme.